Well, hello again, everyone. Welcome to our discussion of section 8.2. Like I was referring to this back when you watched the video for section 8.1, this section 8.2, at the time of this recording, I am not sure if the coordinators would include this section, so I'm recording it just in case they do, but or they might include portion of it, not all of it, because a lot of this material you will probably not see anywhere else. It doesn't have any use anywhere else in trigonometry or other areas of mathematics unless you get to some special topics. So keep that in mind. I think that when we talk about graphs of special polar equations, probably the circle is the most important one, and then the cardioid, n-leaved, and two n-leaved rows, test of symmetry, and lemmason. These last four may not be as critical, or it may be optional. Obviously, if they say, if the coordinator decides to exclude this section, then you won't even see this video. So I'm recording it just in case. So if you see this, if you're seeing it, that means that the coordinator has decided to keep a portion of this, at least, if not all of it, for the course, in which case I will clarify it when we have the course together. Okay, so given these topics, we want to let's start with something easy. So let's do a sketch. So this whole section is about graphs of various special polar equations. So sketch the graph of this equation, theta equals 5 pi over 6, and express it in rectangular coordinate system, or in rectangular form, not coordinates but form. So that. Okay, so we want to sketch this first. Can you see, before I draw this, can you see in which quadrant this will be? If you don't see it right away, do you know how we can easily find that out? Right? We can easily know that because if this was 6 pi over 6, the 6's will cancel out and we would end up with pi. So we would be here. Oops, sorry, let me move this up a little bit. So if this was 6 pi over 6, it would be pi. But it's slightly smaller than 6 pi over 6, right? It's 5 pi over 6. So that means we're not at the end of the second quadrant. We are in the second quadrant. So we are here. Okay, so let's draw that angle. Like that. So the angle that we have here is this angle, which is theta equals 5 pi over 6. Then they're saying, so, and let's call this r, right, r. So the polar coordinates for this side, or this angle and this point, are r comma 5 pi over 6. We know that. Now, we've sketched the angle, but they want us to express this equation, this whole equation, which is in polar form, right, in rectangular form. Okay, so we know that from well, first of all, this angle, we knew that, well, I guess I can write that down first. So the reference angle for this theta, original theta angle, is theta r, or reference angle, is equal to pi over 6, right? The angle between the x-axis and the terminal side of that angle is pi over 6. So we know that from the polar coordinates, we know that tangent of, so we know that tangent of theta is equal to y over x, right? We can translate that into the reference angle. So that would be y, or the opposite over the adjacent. Okay, so let me actually mark that. So it would be this. So this would be y over x, which is this distance. Okay, so you know that the cosine, sine of, or all the trigonometric function values of this angle are equal to the trigonometric functions of this reference angle in the second quadrant. That's the thing you have to watch out. The magnitude of theta equals 5 pi over 6 and theta reference angle pi over 6 is going to be the same, the magnitude, but the sign of it, it's going to be different depending on where we are in each quadrant. So if you're here, it's going to be positive. If you're here, it's going to be positive over negative, so it's going to be negative. If you're here, it's going to be positive because that's negative divided by negative. And if you're here, again, it's going to be negative because you have you have negative over positive. Okay, so tangent of theta, because we know 5 pi over 6 is in the second quadrant, so we know, and it's equal to, let me bring this back, our reference angle is pi over 6, which is that angle that I drew in blue. So tangent of pi over 6, or 30 degrees, is square root of 3 over 3, right? Tangent of pi over 6, which is the reference angle we have, is equal to square root of 3 over 3. But this is in the first quadrant. We are in the second quadrant. So what is the sign of tangent there? It should be negative, right? Tangent is negative. Why? Because tangent is equal to sine of x over cosine of x. In the second quadrant, sine is positive, cosine is negative. So positive divided by negative, it's a negative value. So we have, so therefore, all we have to do is minus minus square root of 3 over 3. So the reference angle is square root of 3 over 3, but minus because we're in the second quadrant, not in the first quadrant. So minus square root of 3 over 3. We know that for the tangent of that angle. Okay? That is equal to that. But why did I take tangent? Why not sine? Well, the reason is that we have a relationship between the tangent of theta and the rectangular form. So, which is, we know that tangent of theta is equal to y over x, right? This is from section 8.1. We know that. If you look at the notes for that section 8.1, you'll see this relationship from the right triangle that I drew, right? Okay, so now set these two equal to each other. This is the general case. This, what I have here, is specific to this problem. What you see at the bottom is the general case for all polar coordinate, polar angles. That has that relationship between tangent of theta and these rectangular values, x and y. Okay, so let's set these equal to each other. So therefore, we can set negative square root of 3 over 3 equals y over x, right? We can say that. From the specific to the general, we can set the two sides equal to each other. These are equal. And so now we can cross multiply once again. So then we can write, if you cross multiply, you get 3 times y equals minus square root of 3 times x, right? And then divide both sides by 3. What do we get? We get y equals minus square root of 3 x over 3. That's what we get. Or if you like, you can leave it at that, as that, or y equals minus square root of 3 over 3x. Either way, that's the same thing. So this is the, so we had the polar form. We converted it to the rectangular form using this relationship, Okay. Okay, so let's look at another example. Suppose we want to convert, or so in this example, once again, we want to sketch the graph of this equation, this polar equation, r equals to 2, and express the equation in rectangular form. Okay. Well, from the formulas we discussed in section 8.1, we know that r squared is equal to x squared plus y squared, right? So we know that. R squared is equal to x squared plus y squared, right? So then let's square this. Let's square both sides of this to get the left side to be r squared. Okay? You can leave it as that, but you'll end up with a radical expression. So it's maybe preferable to not have that. But it's not inaccurate, but the equation looks better if it doesn't have any radical expressions in it. That's all. So we know that. So in squaring both sides. So the solution starts here. So squaring both sides. Both sides of r equals 2, right? We have this result. We have r squared equals 4, right? Squaring both sides of that. But r squared is equal to that. So let's substitute for r squared with x squared plus y squared. X squared plus y squared equals 4. And that's the result. If you've worked with circle equations, you know that that's a circle equation, right? We did a little bit of it, not much, in Math 126. Okay, so we can draw this. This is a circle. What is the radius of that circle? Do you remember how the circle equation of a circle works? What is the radius here? The radius is 2, right? So you knew that from here, but in the rectangular form, that is just the radius, the length of the radius squared. Okay, so we can draw a picture for it. Notice that this one, it says just the r is equal to 2, but it didn't give us any angular value. So we could draw a circle of radius 2 and be done with it, because if we are free to choose any angle for this length of r, then it could be all those infinitely many angles that we have in the circle. Okay, so then we can say that that is the circle, and r, or radius, is equal to 2. So that's the rectangular form. And that's the sketch of the graph. So in general, we have a formula, a couple of formulas that lead to the graph of a circle. So let's talk about that in here. So this is pretty, I think, important in this section. So in general, up. Equations of the form of these two forms, r equals 2a sine of theta and r equals 2a cosine of theta. These are circles. So I will just, so the graphs of equations of this form are circle that has radius equals absolute value of a, the same thing here, a circle that has radius equals absolute value of a, and center at for the sine one, it's centered at a comma pi over 2, and here if you have that equation, then that's a circle with radius that absolute value of a with center at a comma 0. So this is pretty important. So I want to box this. And draw a divider here. So we have that r equals 2a cosine theta leads to a circle with the radius of this length, absolute value of a, because distance is always positive, and center at a comma 0. And for the sine version of that, we have radius at absolute value of a, which is the same thing as with the cosine version, but the center here is at a comma pi over 2. Okay, so having that in mind, let's see an example that makes use of this. So here we want to sketch a graph of the this polar equation, r equals 6 sine of theta, and express the equation in rectangular form. Okay, so we have the r, first of all, is equal to or r squared is equal to x squared plus y squared, right? So we know that here, so here's the solution, starts here. So we know that r squared equals x squared plus y squared, right? So let's multiply. Where do I want to do that? In rectangular form. So I will do that later. Let's do that later. I will do that later. But for now, let's compare this with this form. This is the sine version. So r equals 2a sine theta, and we know that, and also that r equals 2a sine theta matches what we have. So if you compare this with this specific example of a polar equation we have, then 6 equals 2a, right? So let's set that equal to each other. Or 2a equals 6. And from here, we know that a equals 3, right? So now this, for the angle of here, so let's see what we have. So r theta, is there a, yes, so this means that the circle we have, so because of this, thus the circle that we're going to draw this sketch of this, right? So the radius is absolute value of 3, or 3. That's the length of the radius. And the center is at this, right, from the formula. the radius is going to be length A, which we just calculated. 6 equals 2A, so A equals 3. And the center of that circle is going to be at that A comma pi over 2. So center at 3 comma pi over 2. So now we can sketch this circle. Let's do that. We have x, and we have the y-axis, like that. So if the center is at 3 comma pi over 2, this vertical axis y, that is pi over 2, right? So let me write that here. Pi over 2 is that angle. That angle is pi over 2. So the center is at 3 comma y over pi over 2. So that would be, let's see, A, and that's the radius. This is not x comma y. This is not, guys, this is not the rectangular coordinate system, right? This is r comma theta. Let me it just occurred to me. So r comma theta, right? This is not x comma y. These are polar coordinates. So r comma theta. Theta is pi over 2 along the positive side of the y-axis, and the radius is 3. So if we put, say, a dot here, and we say that is 3, then that is r equals 3. So we can then draw the circle by having the center right there. Radius at r equals 3, and with pi over 2 at the for the center, which is that 3 comma pi over 2 is that point. Okay, so let me write that 3 comma pi over 2 is the coordinate of that point. If that's the center, then the radius is 3, so we're going to go a circle like this. Maybe I should, well, I'll use one of my pens here, so let me use that one. And so we go with this. So I'll try to, roughly that's 3 and this is 3. So I'll try my best to do a half decent job to here, like that. So that's the circle with the center at 3 comma pi over 2 and radius 3. Okay, so let's look at another example. This example is a little bit, next one is a little bit odd, but I didn't want to toss it out. I wanted to keep it so that you see one or two of these odd ones too. So we want to sketch a graph of the polar equation theta equals minus pi over 2. Okay, so that's definitely not a circle, right? So it doesn't involve sine or cosine, which is in polar coordinates, I mean. It doesn't have sine or cosine like these forms, which lead to circle with radius a centered at that. The 2a cosine theta leads to a circle, radius this length, and center at a comma 0 in polar coordinates, right? So that, I mean, I should add, well, I don't want to, but that's r comma theta. Okay, so that's not a circle. It's going to be a vertical line that goes through minus pi over 2 as if we had x equals 2, right? So it's a vertical line. All right, so if we had x that. And we know that pi over 2 is here, minus pi over 2 is here. And so this is pi over 2, this is minus pi over 2. So theta is minus pi over 2. So the sketch of our angle here would look something like this. So it would be, I'm just going to thicken this line, this y-axis, to indicate that that's, so it's that, just that. That's theta equals minus pi over 2. I'll write it here. Theta equals minus pi over 2. Okay, so now I said it's odd because when we decide to so sketch the graph of the polar equation and just like before and express the equation in rectangular form, I should have written that, and express the equation in rectangular form. Okay, so we know that the connection between theta and the rectangular form is through the tangent, right? So let's write that down. We know that. We know that tangent of theta is equal to y over x, right? This is, we know this from section 8.1. Okay, so then if theta is equal to negative pi over 2, what happens? So let's plug it in here. Tangent of negative pi over 2 is equal to y over x. Well, I want to actually, so let me, because tangent is equal to sine of that angle divided by cosine of that angle, right? So I want to demonstrate something here because the denominator is now going to be 0, but I want you to see why. So tangent negative pi over 2, this is from way early in the semester, is equal to sine of negative pi over 2 divided by cosine of negative pi over 2, and then let's set that equal to y over x. So I just use this formula we have to insert what we know for the tangent of an angle. So now we have this equals that. Okay, the only reason I did this to show you that cosine minus pi over 2 is 0. So x equals 0. Okay, so the equation, so actually the tangent minus pi over 2 is undefined. So we can say that. So because, I hope I can fit all that here, because cosine of negative pi over 2 is equal to 0, then tangent, then tangent of minus pi over 2 is undefined. Undefined. So the rectangular equation for this, so the tangent of that is undefined. But we do have a rectangular equation for this, right? What is the rectangular equation? X equals 0, right? We know that x is going to be 0 because cosine of minus pi over 2 is 0. So x equals 0 is our rectangular form. So therefore, let me, how can I write this? So I'll write it in red because it's getting really crowded here. So the rectangular equation, rectangular form, that one, is equal to x equals 0. That is the rectangular form. Okay? because tangent of that angle is undefined, so x must be 0, and then y doesn't matter, right? The value of y doesn't matter. The equation is x equals 0, but we knew that looking at the graph, right? That's the y-axis, which is x equals 0. So I thought I bring this up as one of the examples. Okay, so then next, let's do, let's do another example here. We want to so in this example, we want to sketch a graph of the polar equation r equals cosine of theta. Okay, so let's see. I will bring back what we had earlier. This one, this is r cosine theta, right? Compare that with this equation. So let me write, and well, we're gonna let's see. So and sketch the graph of this, and so like that. So yeah, we want to sketch this. Okay. And we can do we want so r cos cosine of theta like that. Okay, so we know that. I'm just gonna write it down here. We know that r equals 2a cosine of theta is the general form, polar equation form for the equation of a circle, right? So what is the radius? The radius, and compare this with that. So 2a in our case is equal to 1, right? So let's write that down. So 2a equals 1, and that means that a equals 1/2. So this circle that we want to draw has radius, so therefore the radius is equal to absolute value of 1/2. Okay, and the center is at a comma 0. A is 1/2, 1/2 comma 0, and this is of course the polar coordinate, right? So this is equal r comma theta that we have. Okay, so let's draw this. Have so x and y, and then so we have that, and then 1/2 comma 0, that's the theta is our angle. Let's move that up, and 1/2 is the radius. So we're on this x-axis, the center is on this x-axis, and if this is, let's say if that's 1/2, which is the length of the radius right there, would be half of that right there. And so that is 1/2 comma 0, 0 being the angle is 0 on the x-axis. So we're here, and the radius is 1/2. So I'm going to draw this as, I'll try this to draw this as best as I can. Not too bad, but not great either. So that, the coordinate of that point, the center, is 1/2 comma 0, with theta being 0. So again, this is not x comma y, guys. So please don't mix this with x comma y. This is r. R is 1/2. Theta is 0. Okay. The rectangular form of this would look odd, but we can write it. So if we add and write the and write the rectangular form, if we add that to that, we can multiply both sides of this by r. So we can say, let's start with that. R equals cosine of theta, and multiplying both sides by r, then we have r squared equals r cosine of theta, right? What do we know about that? We know that this side is equal to, well, we know that r squared is equal to x squared plus y squared. We also know that r cosine of theta is equal to x, right? So let's substitute in this equation with these quantities. We have x squared plus y squared equals x. With that, so then let's bring this to the left, and that's why I say this is kind of an odd form of an equation, but x squared minus x plus y squared equals 0, like that. Okay, like that. And so x squared plus equals x. Okay, so we know that the so this one, okay, so using the completing the square method, we learned in which class? Do you remember? We learned in Math 126, right? So I say, do you remember? It's because just to remind you that all of math is connected, and this is connected to what we've learned in the previous courses. So completing of the square method said that if the coefficient of the quadratic term is 1, then we can write these two terms in a perfect squared form. We're going to get an extra term, which then we subtract and come up with a perfect square a perfect square term for the x and a perfect square term for y, and that'll tell us, the rectangular form tells us, or should tell us, exactly what we already know, which is the center of that circle is at 1/2 comma 0. So when we're done with finding the rectangular form of that equation, it should tell us exactly what we know. Let's see if it does. So I'm going to come up here to write the, to use the completing the square method. So factoring out, or we don't need to factor, so the middle term, whatever that coefficient, the coefficient of the quadratic term, I'm just trying to remind you of what that method is from Math 126. If the coefficient of this quadratic term is 1, then let's divide the middle term, x term, by 2, right, which is -1. And so -1 -1 divided by 2. Okay, so that's, then after that we have our equation. So we have x, that same thing. Some of my students in Math 126 had a brilliant idea. They said, oh, that's just b divided by 2, and that's correct. So b divided by 2, which is this. b divided by 2 is that, -1/2, right? b, if you think back to the quadratic equations, that's a is 1, b is -1, right? So b divided by 2 is -1/2, and then x minus 1/2 squared. So we solved one problem, we created another problem. The problem we solved is now we have been able to write these two terms as a perfect square, right? X squared minus 2 times 1/2 is minus 2 times x times 1/2 is minus x. So we got it. But we generated a term, extra term, which is 1/4. Right? So we have 1/4. So this, if you expand this, you're going to get these two terms. If you expand this, you're going to get these two terms plus 1/4. So we need to get rid of that plus 1/4 because there's no 1/4 here, right? So by saying minus 1/4, this will balance that. This minus 1/4 gets rid of that plus 1/4 that we generate when we completed this square. Okay? And y squared is okay because it's already a perfect square. So plus y squared equals 0. Okay, so now let's clean this up. We have x minus 1/2 squared plus y squared equals 1/4. So that's the rectangular form of, so this is the rectangular form of that equation, this equation, which was the polar form, right? It's so right there. So let me right here, this is the polar form, and that is the rectangular form. So from the polar form, we knew that the center was at 1/2 comma 0, 1/2 being r and 0 being the theta. Do we get that here, the rectangular form? Absolutely, right? If you compare this with the general, so compare this with the general form of equation of a circle, which is x minus h squared plus y minus k squared equals r squared, what do we get from this? Is going to be, it's the same thing as what we got from the polar form, right? The center is at 1/2, comma 0, but this time this is x, this is y, because we're dealing with the rectangular form, and radius is 1/2. And r is equal to 1/2, right? Because that's r squared, so r is 1/2. So yeah, we got the same thing from the rectangular coordinate as we did from the polar coordinates. Okay, maybe I can fit, it barely fits on the screen, but I hope you can see it, barely. So that's the polar form, and that's the center at 1/2, comma 0. And this is the rectangular form, 1/2, comma 0, once again, is the center with radius at 1/2. And we got A was 1/2, right? That's, this distance is 1/2. Let me write that. So this distance is r equals 1/2. Okay? Okay, so let's see. Okay, so the next topic, it dives deeper into special graphs. I'm thinking that the coordinator of the course would want this material included, so what we did so far, up to page 4, and maybe they'll say exclude what comes next. So anyway, I don't know that at this point, so I will cover it. So I will say that this is sketching the graph of a cardioid, and this is, and let me just say optional at this point. So that means you'll hear from me whether this topic is included or not, which I will ask about from the coordinator of the course. So here's the graph of a cardioid, looks like this. So is a heart-shaped, not almost like a heart-shaped figure. And in general, so here's what it looks like. So x, y, I will try my best to draw this as best as I can. It's not an easy graph to draw. So it'll go something like this, and then like this, like that. Okay, it looks like that. And that is a heart-shaped figure, and this is the equation of a, so it has a special equation, and they are as follows. So R equals A plus or minus A cosine of theta, and then R, I should say this or that, not both. So either that or this one on the bottom generates a cardioid. Either that or the one that I'm writing, A plus or minus A sine of theta. Okay? So either that or this So cardioid is generated when, in this equation, theta goes from 0 to 2 pi. Okay, 0 to 2 pi. So you take this equation, you give A some value, let's say 2 or 1, and then theta will trace that cardioid going through 0 to 2 pi when it goes from 0 to 2 pi. So let me label this graph a little more. So this part of the cardioid is 2a from the origin. That point has coordinates 0, comma a, and here this is so 0, comma minus a. Okay, here, there. So that's a cardioid. And so let's do an example of sketching a cardioid. We want to sketch the graph of the polar equation, which is r equals 2 minus 2 cosine of theta, right? So we have that one, this top one, we have that. So A is equal to 2, right? A is equal to 2. So A equals to 2, and here's the graph. I should move this up. I'm off the screen there. Okay, like that. Like that. Okay, so we have okay, so this would trace like this. Like that. Not too bad, but not great either, right? Not too good either. So then these points, that's going to be 2 or 0, comma 2. Or I'll just leave it at that. That's and 2, and then this would be minus 2, and this, of course, is negative 4. Or negative 4, comma 0, that would be 0, comma 2, and this would be 0, comma negative 2. Those are the intersection points, or the x and y intercepts. Okay, at that. So let's look at the graph of a rose. The graph of a rose, and I'll quickly write that this is also optional. Okay, like that. All right, so a rose looks like this. And it has certain trigonometric equations that draw a rose. So as a matter of fact, let me write down the equations first. So in general, of the form, one of these two forms, either r equals a cosine of n theta, or r equals a times sine of n theta. That, in general, that gives is an, this is important, n leaved, number of leaves in the rows, n leaved rows if n is odd, something like 1, 3, 5, 7, 9, something like that. If that n is odd value, then we have that many leaves. So if it's 3, we got 3 leaves. If it's got 7, if it's n is 7, then we got 7 leaves, and so on. But if it's even, or, so that or is, so that's 1 and this is 2. I'll just turn these into bullets like that. Is a 2n leaved, 2n leaved rows if n is even. Okay, so if n is even, something like 2, 4, 6, and so on, then the number of leaves are double that. So 2 times 2, 4. If n is 2, then we got 4 leaves in the rows, the graph of that rows. If n is 4 in that equation, if n is 4, then we've got 8 leaves to that rows, and so on and so forth. I've done this on a computer, actually, using the open source software called GeoGebra. You can actually draw these and look at them. You can download GeoGebra. If you decide to do that, it'll allow you to look at these graphs. They're pretty neat. And if you download GeoGebra, if that's at all what you are interested in, it'll give you the option from which site, which global site to download it. The most up-to-date version is always on the server that is in Austria. So there are various servers. When you download the software, it'll show you that. Pick the one that is based in Austria, because that's the most up-to-date version. And this is for those of you who'd like to look at these graphs on a computer. So there's a free software that'll let you do that. Or you can just Google. You can Google the graph of a rose and in trig, and it'll come up. Okay, so this is what it looks like, and I want to put these here in a box, these important formulas. And here's a graph of that. I need to move this up. Like that. And so we have, what happens is we're going to have, I'm going to try to dissect each quadrant with a dashed line like that, and also like that. So like that. This, and then we have so here is, so for example, that would be one of the petals of the rose, and like that. These should be identical, but obviously I can't do it. So, and then this one like that, and then finally another graph like that, okay? And then these are, so at the A that you saw here is wherever you see the intercepts. So here, here, and here. So this would be A, minus A, minus A. Okay, and these dashed lines are dissecting each pairs of quadrants. So this has to be, the theta for this has to be pi over 4, and the theta for this has to be 3 pi over 4. That's just the equation of the, or that angle is 3 pi over 4. Okay. So then, knowing that, let's sketch the graph of a rose. So here's an example. Sketch a graph of the polar equation r equals 2 cosine of 3 theta. So in this case, if you compare this, well, let me write down, so solution, right? We know that, I'm just going to write that, it's off the screen now, but I'm going to write it here. We know that r equals a cosine of n theta draws a rose, right? So, and based on this, then r a is equal to 2, right? So a equals 2, and this n is odd. So n equals 3, that's odd, so we have 3 leaves in this rose that I'm going to draw, given this criteria. Okay, so maybe I should box that whole thing. Here, all the way here and here, right? So we have n, in our case, is odd, so we're going to have that many leaves, or 3 leaves. Okay, so let's draw that. I'll draw it here. Okay, so we will have like that, like this, and like that. Okay, and wherever you have the intercepts, so here you have 2, and you have -2 here. Obviously, these are off the axis like that. Okay, so that's the rough sketch of that. So tests of symmetry, this is once again an optional topic. So meaning that I will wait for the coordinator to tell me if this is required or not. So for now, I'm making it optional. So if a polar equation that we have, if a polar equation is the same for theta, and negative theta, what two functions we know that could do that? And minus theta. Remember which two functions? Cosine and secant, right? So then the graph is symmetric about the polar axis. What is polar axis? It is the x-axis. Okay, the same thing. So let's draw a quick graph of this for part A. I'll just draw it here. And so we could have, so if we have a shape like this, like this, and like this, like that, roughly like that. So then we have this angle here from here. So that would be r comma theta. And this would be my graph isn't that symmetric, but it should be. So if this was perfectly symmetric with respect to the polar axis or the x-axis, you would have this r comma theta, r comma negative theta, and that would be theta that is minus theta, right? And so that's that. That's for that, for part A. For part B, and that's if the polar equation doesn't change if you go from theta to negative theta. Then you have a graph that is symmetric with respect to the polar axis. So then the graph remains, or if the graph is the same for when we replace r by minus r. Then the graph is symmetric about the pole. About the pole. Pole meaning the origin, right, in the polar coordinate system. So the graph for that would look like something like this. Like that, and we can draw a line right through the middle of this, like that. And that point here, that point has coordinates r comma theta, and the coordinates here are minus r comma theta. Okay, the opposite. Okay, so for part C, so this is all cases of tests of symmetry. So one more case. So case C is if a polar equation is the same again, and when we replace theta by pi minus theta. Okay, so we replace, in a polar equation, we replace theta by pi minus theta and it stays the same. And so then, if that happens, then the graph of that polar equation is symmetric about the vertical line or the y-axis vertical line. Okay, vertical line, let's just say vertical line theta equals pi over 2. Okay, or not pi, sorry, theta. Vertical line theta equals pi over 2. Yeah, that's correct. So here's what the graph would look like for something like that. So again, I'll do my best to draw this as symmetric as I can, but I don't think I'll do that great of a job on this. So like that. So with respect to the vertical line, and then so if we have point here, then the symmetrical version would be on this side. So if this is, so this would be r comma theta. This is theta comma theta equal pi over 2, this line or this angle. And so this would be theta, and then this would be, this angle would be pi minus theta. Okay, use that. And then finally, the limison. So the graph of, so sketching the graph of a limison. Okay, so a limison has this general equation. In polar form, of course. So we have r equals a plus or minus b cosine of theta, and r, or not both, but or either that or r equals a plus or minus b sine of theta. Okay, so that's for limison. And here is what the graph looks like. I'll draw it here in this blank space. So this will be, let's see, I'll start from here. I didn't draw this correctly, but let me correct this with my thicker marker. So this comes here, goes through the origin or pole, comes back, goes through it again like this, and goes through here. So please ignore that one. The thinner line, ignore that. It should have come through the origin like that and gone back out like that. Like that. Okay? So here, so this is the graph of R equals, or R equals 1 plus 2 cosine of theta. Okay. All right. So one last thing, I should have actually mentioned this last note in the, before these special graphs. So once again, this is optional. So I'm going to put in parentheses here, this is optional. And so then this note is pretty important, and I should have mentioned it before these special graphs of Rose and Limassol and the cardioid. It should have come before, but it's here. It's still okay. It's not too late to mention it. So in the zeros of the function y equals f of x, so correspond, this is something we know, right, in rectangular coordinates, correspond to the x-intercepts of the graph, right? We know that. We've already know that. We already know this. So let me, this we already know from before, from Math 124, Math 126. So in if you have rectangular coordinates, the zero of a function is simply the x-intercepts, right? So you plug in for y with 0 and find the x-intercepts. In polar coordinates, so here, in polar coordinates, the zeros of the function, r equals f of theta, are the angles theta at which the curve crosses the polar axis. Okay. Right, so 0, Yes, so polar axis. So just keep that in mind. We already knew how to find the zeros of the function when we had in the rectangular coordinates, but that same idea translates into the polar coordinates, and the zero of the function is the theta, not the value of x, but the theta at which the curve crosses the polar axis, which is the horizontal axis. Okay, so with that, this wraps up section 8.2, and thank you for persisting through this. And so again, if you're seeing this video up there, that means the coordinator has approved at least a part of this video to be in the course. And I will, if not all of it is included, then I will make a remark right under the video saying from here to here is included and from here to there is not included. Or I might just edit the video. I could do that too. I could edit the video and cut out the portion that you don't need to see, in which case you don't have to worry about any of these special graphs. Okay, have a nice day, and I'll look forward to see you all next time.